All right, y'all, it's in the title. We got to go fast. I ain't singing for you today. We have business to attend to. This business is the discrete Fourier transform. This is going to be the math that we've been doing for the last week or two and moving it into computational space. How do we discretize this? How do we take analytical math, convert it into bytes and discrete numbers, and do these operations on a computer so that we're not calculating things by hand until the end of time? This is going to be the last example this semester of this theme that we've been dealing with, which is okay, but how do you do the math on the computer? And what we need is a way to take these continuous functions and chop them up into pieces, work on those pieces. Before we do that, though, I do want to talk about application. So here's my why it matters. We're going to get this out in front. The Fourier transform infrared spectroscopy technique is a materials characterization technology, and it's right there in the name. Fourier transform must be relevant. What is going to happen here is that we are going to take a specimen of material. So here's our material, and then we are going to put it on a surface with a little transmitting crystal. We're going to pump infrared light into that crystal, and that light is going to come in, bounce around a whole bunch, and then some of it will come out. But not all of it comes out. Some of it gets absorbed by our material. And which frequencies of infrared light get absorbed are dependent on the bond structure of this. So this is the purpose of this technique, is to understand what bonds are present in a substance. This lets us gives us information to help figure out the molecular structure based on the bonds that are present. So what we get is a measurement of intensity as a function of time, blah, 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 blah. But what we want to do is we want to do the transform of this and ask, okay, that's cool, but what frequencies of light were absorbed by the material? Because that's what tells us about the bonds, and we do that with the Fourier transform. And then you get results that look kind of like this, where we are plotting frequency on the horizontal axis, and then we are going to be looking at the intensity of each frequency. So this is saying that, oh, around this value, there's a lot of absorption, and that means that there's a bunch of carbon oxygen double bonds in my material, and that the stretching vibrations of those bonds. That's the normal mode of bond oscillation. See, it all goes back to old stuff we did before. Those normal modes operate at certain frequencies, and so this is how we learn about what's in the material. So there's our application. Now, as far as doing the math, essentially what we need to do is to take a continuous function, chop it up into pieces. So if I have like, yeah, I don't know, like this kind of thing, maybe this is my continuous signal. Well, what I want to do is to chop it up. Do, do, do. I'm trying to get this more or less accurate, something like that. And so then these intensities at each point, 1, 1, 2, 3, 2, 1. Like this is my data vector. 1, 1, 2, 3, 2, 2, 1. So like those are the numbers that go in my discretized signal vector. And once I have that vector, I can do math on it. Did we do math on vectors? Yay! Pikachu is so shocked. Because you can never escape linear algebra. It's always there. It's your friend forever and ever and ever. Hooray! And since you know how to do linear algebra, you're good to go. The linear algebra that we're doing is actually just matrix multiplication. So the complex Fourier series that we saw a couple videos ago, you're taking those. So hopefully this term looks familiar from the complex Fourier series lecture. And when you write out all of those series, you realize, oh, I can rewrite this as matrix multiplication because it's a bunch of multiplications and additions happening together. And this matrix is the matrix that when you multiply it by that signal we had, whatever it was, 1, 1, 2, 3, 2, 1, 5, I don't know, something like that. This transformation matrix acting on that vector transforms it from a signal f of time into some new vector that will be the Fourier transform of the original vector. So this is what we're doing. Instead of doing these crazy integrals from minus infinity to infinity of whatever, we're just going to multiply some matrices. That's great because we can do that quickly and because we've invented technologies like GPUs that are really efficient at doing matrix multiplication. This is one of the reasons we love to turn problems into linear algebra problems is so that you can do stuff like this. Now, in terms of implementing it, that's your discrete Fourier transform. There are different algorithms for doing these in more efficient ways for certain kinds of problems, and a really, really popular one is the Fast Fourier Transform, the FFT. And what you're doing is you're taking this matrix multiplication, that's still what you're doing, but you're saying, actually, I don't have to do all of those multiplications because this matrix has symmetries in it. Like those two terms are the same, and those two terms are the same. And when you start to realize, oh, there's a lot of repetition here, you have to do some of the calculations, but then you can just copy paste your answers for a bunch of those calculations. And once you remove all those unnecessary steps, by only doing each unique calculation once, then you save a lot of time. This gets quite fast. I'm not going to get into the algorithm side, but I wanted to make that point that the symmetries of the matrix let you figure out which operations don't actually have to be done because you can figure them out from other pieces of the calculations. It's called the fast Fourier transform. How fast is it? Well, when you do the full discrete Fourier transform, if you just apply the whole matrix, this would take order of n squared computing time because you have an n by n matrix. And so this is the usual behavior that we see for square matrices. But when you realize that you don't have to do all of those multiplications, you can avoid some of them, then the result that you get is that the FFT scales as n times log of n, where again, n is the length of your data vector. Now, I don't know if that sounds like a big deal or not. You're like, well, it's still n times something. It's a little smaller than n squared, but is it a big deal? So here's an example with numbers. If you have a signal that's 4,096 samples long, which is really quite small, then doing all the multiplications for the discrete Fourier transform, that would be give or take 30 million-ish calculations. Fast Fourier transform takes only 70,000 to get the same answer. So this really is much more efficient, especially as you get to bigger and bigger signals. Imagine that you have like an entire song that you want to process, or that you're looking at a X-ray diffraction data set that has millions of data points in it. This is going to very quickly scale, and it saves you a lot of calculating time. So if, for example, you were to look at what the output looks like from a discrete Fourier transform, these are the sorts of things that you see. This original signal is just uh, cosine of 10x plus cosine of 20x plus cosine of 30x, 40x, 50x. And so what you would expect in the continuum problem is that you would get delta functions at 10, 20, 30, 40, and 50. Those are the only frequency components of this signal. And then when you do the DFT of this thing, then that is pretty much what you see. You see, oh yeah, there are these spikes at 10, 20, 30, 40, and 50, but the function itself is choppy. It really shows these results of having been discretized, and how smooth or how continuous this looks depends on how many samples you take in your original thing. So as so many other calculations we've done this semester, if you take your continuous function, cut it up into a bunch of tiny pieces that are very closely spaced, you will get smoother and usually more accurate results. But again, that scaling n log of n, you need to keep that in mind because as the numbers get big, your calculation time gets really big. All right, that's all I wanted to say. I just wanted to introduce the concepts of discrete Fourier transforms basically, and now Mia is going to show you some application in code to see how this comes out in Python. Tragically, we're almost at the end of the semester, but we will be doing one more application day after this, and so I hope that that will be a good time, and that's how we'll wrap things up. Okay, I'm going to hand it over to Mia.
Hello everyone, welcome back to another short little Mia lecture. I hope you're all doing well and you had a good break. Today we're going to talk about Fast Fourier transforms in Python. So as you saw in the last lectures from Tim, we love Fast Fourier transforms, and now we're going to do them in Python. So there are two ways to do this. One is that you can read in a signal and take the Fast Fourier transform of it, or you can read in an image and take the Fast Fourier transform of that image. Today, we're just going to talk about how to take the Fast Fourier transform of an image rather than just its own signal, because doing the Fast Fourier transform of a signal is pretty easy by itself, and I believe in you all to do it. When it comes to actually using images, that's what we're going to focus on today. So our first example is we're going to look at a square potential well. This is a signal you might have seen before. I'm going to cheat a little and show you the bottom so you can just see what this looks like. This is a square potential well. At least this is the one we will be analyzing right now. So that's what it looks like. It's got a few little square humps in it. And yeah, so if you read in this image, which we have done here at the top of this code, using this module CV2, I would really recommend looking further into CV2 for those of you who like to do photo manipulation or also like extracting patterns from photos, which is really helpful in data analysis. It's very, very helpful in that realm. So look into it if you haven't already. But continuing with this, we load in the image and we change it from its already color to grayscale. This will be important in a little bit, but then we plot that image. Now we get to the actual part for prepping it for taking the Fourier transform. Since we just want to take the Fourier transform of the signal, what we need to do here is we're actually going to choose a row. Just one row of the pixels so that we are only using one dimension instead of two. Then with that, this is just finding the middle row since we're taking the shape and dividing it by 2. Then we're going to actually call that row the signal by taking just that row and all of its information in that column. Then we do 255 minus the signal. The reason why we do this and replace that value, the reason why we do this is because it's just to make the signal brighter in the image below, which you will see in a second for actually a later plot. Don't worry about it too much. Then we're going to plot this signal, so just that row, so we can see that. And then we're actually going to take the Fast Fourier transform. When we take the Fast Fourier transform, there is a good implementation that you can do, hint, hint, by yourself for just doing Fourier series. However, for Fourier transforms, there are nice packages. Not that there's not nice packages for series either, but that's easier to do by hand. For Fast Fourier transforms, though, it's much, much nicer to use the tools that are already built for us. So NumPy has a tool. We have NumPy and then .fft and then FFT for the 1D transformation and then of this signal. And then so we can actually have the plot of the frequency. We do np.fft.fft frequency, and we do that of the length of the signal. So here is what we get from plotting all of those different things. So here's our square well potential, which we've already seen before. Now we actually have 2 more plots. This is the signal. So again, looking at maybe that middle row, it's going to be somewhere around 60. If you draw like a little line across and you see what it'll be analyzing. So there will be like nothing, 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 and then it'll hit this, and then there will be big signal because it'll recognize that something's there, and then the same thing, and then oh my gosh, there's something there. And then it'll keep happening for all of those distinct points. And you can kind of see, so this is going to be like around 60. This is going to be around like 125. And if you actually look at the signal, that's exactly where you are getting these peaks is it's this where it's recognizing that there is something there. And then when you actually take the fast Fourier transform of this signal, you get this magnitude spectrum. So why this matters and what these physical curves actually means, because you might be looking at this and you're like, okay, I don't understand what I'm looking at. Um, a square well, the FFT of a square well potential are Gaussian curves. And even though these are like very rough estimates, you can kind of see the bell-shaped curve. It's quite hard for Python and just in general for them to do like an exact bell-shaped curve estimate here. But you can see how even connected together, you can still see that up and down kind of motion for each of these. And that's exactly what we are expecting to see. Good job. Next part, we're going to talk about how to do this for a sine wave. Very similar implementation. We're going to read in an image I have of a sine wave. Again, scrolling down so you can see it. Here's our sine wave image. Ta-da! Awesome. So we read in that image, we plot it, then we find a middle row, some row in the middle. Find just single out that one row and all of the information with that row, change it so that it's actually different color than it would be. Then we plot that signal that we've extracted, and then we take the fast Fourier transform again. Same exact process. So with this, we have our sine wave, and then I think for the row dot shape here, it actually finds a point that's like a little higher. But what happens is if we go around like 50, like let's say it's that, you'll find a point around here. So that's going to be like, I have no idea what number that is, some number. But then you'll hit another point here, which would be a little over 100. And then here around 300, and then 400, and then here and here. And that's exactly what you get for this signal. So you'll find something here, and then 100, and 300, and 400, and then there and there. So yeah. And then when we actually do the fast Fourier transform of our signal again, we get this beautiful, lovely little curve. And you might be wondering again, like, I really don't understand what I'm looking at. And why is there one big one in the middle? And what's going on? Let's talk about it. So, something that you might remember from the last lecture is that when looking at the fast Fourier transform of a cosine, it is actually the Dirac delta function. Sine works pretty much the same way. So even though it's like a little bit of an approximate, this one for sure looks a little bit more like it, but they are all Dirac delta functions, all attached together. That's why they have these really sharp points. So then, it's just a connecting line. So we have all of those things. Let's talk about another example. So in this example, we're going to look at some lattice points, or quote unquote lattice points. It's really just a grid of points. Yay! There they are, grid of points. So now we're going to do the Fourier transform of an entire image. So here's what we're going to do. We're going to read it in the same exact way using CV2. We're going to convert it to grayscale. So we do this because it gets rid of a lot of the background noise. But regardless, we plot that original image. Then what we do is we use NP again, FFT, but then FFT2. This does 2D FFTs. And we can just put the whole image in there, which is, again, pretty easy. Then what we have to do is we have to shift it. This is because we want it to be around the center of the spectrum, which is something you did just, equation wise. But here, this is how we do it, is we just make a shift. Then We find the magnitude of that shift, and that is the actual spectrum we are plotting. So we have this original lattice, and then we have this. And you might be looking at this and you're like, literally, what am I looking at? This looks like nothing. And I would say, yeah, that's exactly right. It's hard to see. So if we add a little bit of code, this is the same thing, but just zooming in so that we have a little bit of clarity. These are the lattice points, and here is the fast Fourier transform. So looking at this, you're probably like, these look like the exact same image, right? Because we just have points and then we have points. So you might be wondering, what is actually the difference between these two images? Well, if you were to find the distance between 2 points, let's say from A to B, it would be a distance of A, or let's call that, the lattice parameter A. If you were then to try and do the same measurement between 2 points here, that length would actually be 1 over A. So even though these look the exact same, they are actually different because their spacing is different. Because this is in reciprocal space and this is in physical space. Crazy, right? And this stuff is really, really important. I even wrote it out for you. And you'll see why in some later videos. But an important application of this is phonon dispersion. So I don't really have anything to show you for this portion. I'm just going to kind of describe what phonon dispersion is and why this matters here. I've done a little bit of research on this subject. It is really, really important and just one of many big applications in which fast Fourier transforms are important. So particularly for phonon dispersions, when phonons are causing disruptions in a lattice, one way to study them is to look at the phonon frequencies. And in order to get those phonon frequencies, you need to use fast Fourier transforms. I know this sounds a bit abstract. For now, that is it. I hope you guys have a great day, and I will see you all in class.